Good day, ladies and gentlemen. For today's video, let me introduce to you the famous Carnot principle, Carnot heat engine, and Carnot heat cycle. So first, we have here the person who proposed this concept. So he is Nicholas Leonard Sade. He is a French physicist and a military engineer. He is the one who discovered that there is a significant relationship between work and heat. So he discovered that there is a relationship between work and heat. So in 1824, he started formulating his concept about the perfect engine. And this perfect engine now is what we called a Carnot engine. So it was named after Sadi Carnot, or after him. And we'll be tackling that one later in this video. So his discoveries lead to the development of the second law of thermodynamics because of this Carnot cycle. This idea of Carnot cycle, the formulation of the second law of thermodynamics has been created. So basically, the foundation of the second law of thermodynamics is the Carnot cycle, which this Carnot principle has based on. So first, let us discuss what is Carnot principle. So Carnot principle is there is a theoretical limit of all cyclic devices. That is the second law of thermodynamics. This means that there is a maximum efficiency level of all operation in cyclic devices, like the maximum efficiency of a heat engine. And this maximum efficiency is the product of a reversible engine or a reversible process. So this maximum efficiency is the product actually of a reversible process. So we'll discuss that one in the next video or during this video. So the first principle is the efficiency of an irreversible heat engine is always less than that of reversible engine operating between the same reservoir. So the first principle means that all real life cycles with our irreversible will have lower efficiency than a reversible engine operating between the same reservoir. So it is impossible for any irreversible engine to have an efficiency higher than reversible engine. So basically, reversible engine is higher than the efficiency of our irreversible engine. So the second Carnot principle is efficiencies of all reversible heat engine operating between the same reservoir are the same. So the second principle states that all reversible heat engine which operates the same temperatures of source and sink will have the same efficiencies. So that is the Carnot principle. So what do we mean by reversible process? So reversible process simply means that the direction can be returned to its original state or position. So this reversible process can redirect its direction to its original states. That is reversible process. As a result, Carnot principle puts an upper limit on the efficiency of a reversible and reversible engine. So today, the idea that the efficiency of a heat engine is a maximum when the engine operates reversibly. So that is now a Carnot principle. However, this does not imply that the reversible engine will give you a efficiency of 100%. So basically, it is just a theoretical number, or it's just a theoretical limit. It has a theoretical limit. So that is now. The second law of thermodynamics is derived from a Carnot cycle, which this principle is based on. So Carnot principle is another way of expressing the second law. So the second law of thermodynamics is actually expressing through this Carnot principle. So that is the two Carnot principle of thermodynamics according to Sadi Carnot. So now let us discuss a Carnot engine. Now let us look at a Carnot heat engine. So it is a heat engine that is based on Carnot cycle. So actually, Carnot engine is actually based on Carnot cycle that is proposed by Carnot Sarde. So it converts the maximum amount of energy into a mechanical energy. So this is a conversion. There is a conversion from heat to produce or yield a work. So second, the efficiency of any engine depends on the difference between the highest and lowest temperatures reached during one cycle. In one cycle, the differential rate between source and sink will give its efficiency. So the higher the difference, or the greater the difference is, the greater the efficiency. So if the difference between the source and sinks is greater, then the efficiency of the system will also greater. So that is a Carnot engine. So these are the different parts of heat engine. This is a hot reservoir, or the source. It's a hot reservoir or source is material kept at a high temperature and having infinite thermal capacity. Any amount of heat can be taken from it without changing its temperature. So when we say infinite thermal capacity, the temperature is constant. The temperature cannot be changed, because this is the source is actually the hot reservoir where the temperature was kept at a high temperature. So that is a source. And another one is the sink. A cold reservoir or sink is a material kept a low temperature and having infinite thermal capacity. Any amount of heat can be given to it without changing its temperature. So the sink now is the cold reservoir. This is the area where the temperature is kept low. So the lower part of the temperature is actually in the sink. So it's another a infinite thermal capacity, because it cannot be changed and cannot be altered. It remains constant. So that is what we call an infinite thermal capacity. So another is working substance. Working substance is a material which converts heat energy into work. It is taken a cylinder fitted with tight, movable, frictionless piston. The lower side of the cylinder will be thermally conducting. So another one is the working substance. It converts a heat energy into work. It must be solid, liquid, or a gas, or ideal gas. Anything that is put under a cylinder fitted tight movable piston. So it is put inside the piston. So insulating stand. It insulates the working substance from thermal contact with the surrounding that is used for performing the adiabatic process. So insulating stand is actually protects or insulates, naghihiwalay sa working substance from thermal contact and surroundings, because that is the role of the insulating stand. So these are the four parts of heat engine. These are the source over there, source at temperature T1, and insulating stand with the color green, and the sink at temperature T2, or the cold reservoir. And this is the piston, ideal gas, working substance, and this is the cylinder. So that is a heat engine. So this reversible heat engine by Sadi is useful for judging the performance of a real engine. So because of this, we can now judge the performance of a real engine because of this heat engine. The important thing to remember about Carnot engine is all input heat originates from a hot reservoir. Here, all inputs comes from the hot reservoir, and all the rejected heat goes into a cold reservoir, or the TC. So here, the heat originates here at the hot reservoir, and it is rejected through the cold reservoir. So that is the important thing to remember about the Carnot engine. So the further efficiency of this heat engine is independent of the working substance of the engine. It can be depend only on the temperature of hot and cold reservoir. So it doesn't matter what working substance you are using into. It doesn't matter what process or what the things matters into it. So it matters between the temperature of your hot and cold reservoir. So basically, it is dependent only to your temperature. So this idea led Lord Kelvin to propose a thermodynamic temperature scale. So the one who proposed the thermodynamic temperature scale is Lord Kelvin. So the efficiency of reversible engine is independent of the working fluid employed and its properties or the type of reversible engine used. So, because all reversible engines should have the same efficiencies. If they are operating between the same temperature limit, which means it doesn't matter what kind of engine you have, the properties you used, as long as they undergone reversible process, and that is the basic of defining the temperature scale of thermodynamic temperature scale that was proposed by Lord Kelvin. So let's take a look here back. So we have here the TH or the hot temperature of hot reservoir. This abbreviation now will help us in solving and finding and solving the problems later on, the mathematical problems later on. So TH is temperature of hot reservoir, the TC temperature of cold reservoir, the QH the heat energy extracted from hot reservoir. It is a heat coming from a hot reservoir, and the QC waste heat refracted or rejected to cold reservoir. So our QC now, this is a waste energy that comes from the heat engine or the heat energy. So here, that is a cold reservoir TC. So the W here on the arrow, this is a useful work generated by heat engine. This is a total work output by the process, by one cycle or during the process. So that is a diagram of a heat engine. So here, as you can see, as I have mentioned a while ago, high temperature source. So the efficiency of a reversible cycle basically depends on the function of two temperature. So just like I mentioned, the hot temperature and the low temperature, or the temperature of your source and the temperature of your sink. So that is a thermal limit of the source and sink. So here, let's take a look at the diagram. It is an example of three reversible process or reversible engine. So we have here the heat engine A, heat engine B, and heat engine C. These are operating between high temperature source and a low temperature sink at T3. So as you can see, the high temperature source here is T1 and T2. Low temperature sink at T3. So in heat engine A transfer heat at the rate of Q1, as you can see, transfer it to the rate of Q2. So Q2, it transfers the rate in the Q2. So to heat engine B, so and heat engine B here, the heat engine B transfer heat at the rate of Q3, as you can see, rate Q3 to the low temperature sink. So at the low temperature sink, so the heat engine A gives an output for work A, here work A, and the heat engine B gives the work output, the total work output of B. So heat engine B is equals to work output B. So so on the Q1 to Q3, and then the total output, which is the QC. So that is a thermodynamic temperature scale in reversible engine. So with using a 3 reversible engine. So hence a thermal efficiency now, we have a formula. Thermal efficiency is equals to 1 minus QL over QH. So our QL is a low temperature, and the QH is the amount extracted from the heat source, and the QL is the rejected or the waste energy. So 1 minus QL over QH. So the thermal efficiency of a Carnot engine or reversible engines can be 1 minus TL over TH. So 1 minus low temperature by hot temperature. This is actually in terms of Kelvin, because if we are using Celsius and Fahrenheit, this will give us a wrong calculation. So we are better use a Kelvin temperature. So as you can see, as we increase the difference between the hot reservoir and cold reservoir, we are also maximizing the efficiency of the heat engine. So like for example, we have a 100 Kelvin to 300 Kelvin. So our hot temperature is 1000 Kelvin, and our cold temperature is 300 Kelvin. So as we increase our temperature, our source temperature, or the energy of the temperature of our source, that will give us a high efficiency. And if we reduce, or we have a lowest temperature, low among the lowest temperature, and that will give us also a high efficiency. So better say, it simply means that high temperature with a lowest temperature will give us a high efficiency. If our source have a higher temperature and our sink have a lowest temperature, then that will give us a high or maximum efficiency or high efficiency. So that is a Carnot heat engine. So here, an automobile engine, for example, would be more efficient if the fuel burned hotter and the exhaust gas came out of the cylinder at a lower temperature. So just like I said a while ago. Yeah, so that's it. So we have here the diagram, and I will be discussing this one by one later in the Carnot cycle. So let's proceed to a Carnot cycle. So this is an ideal cycle for the operation of heat engine. So our Carnot heat engine uses a Carnot cycle. This is the ideal cycle. In one complete cycle of operation, there are 4 different thermodynamic processes. So there are 4 thermodynamic processes. It is in a Carnot cycle, heat energy transferring from a heat source to its sink. So how does the heat source transfer? How does the energy from heat source transfer to the heat sink? So it is composed of 4 reversible processes. Reversible process means the direction can be returned to its original state. These are the 4 reversible thermodynamic processes: the reversible isothermal process, a reversible adiabatic process, reversible isothermal process, and reversible adiabatic process. So that's it. So first, let us discuss the first process in a Carnot cycle is the reversible isothermal expansion. The working substance is kept in contact with the source. The piston of the cylinder is moved outwards. The gas expands at a constant temperature. So this means in a thermodynamic, isothermal means there is no change in temperature. So our temperature will remain constant. So what happens here is that the energy from the heat source is transferred to the working substance like gas from the heat source to a working substance like gas, as it results to gas to expand. So therefore, the gas will expand since there is an expansion, which increases the volume and decreases the pressure. So as you can see, the PV diagram, that is the PV diagram, the pressure volume diagram. It increases the volume and decreases the pressure. So let's proceed to the second process, the adiabatic expansion. This is a point B to C. It is an adiabatic expansion. So what do we mean about the adiabatic expansion? Adiabatic. So adiabatic means there is no transfer of heat between the surrounding and the system. There is no heat involved from the surrounding. So simply, all change in temperature, all change within the temperature is contained within or inside the system. So the change in temperature only contained inside this system, which make the entropy zero. So that's why its entropy is zero. So our volume increases and our pressure decreases since it is an adiabatic expansion. So that is a second process. So let's proceed to third process, which is the isothermal compression. So isothermal compression is the third process. We're at the point C, isothermal. TC. So as you can see, this one, it is an isothermal compression basically, since there is a compression. So there is a compression. What do we say by compress? It is being bound, it's being compressed, squeezed, or something like that. So the volume decreases while the pressure increases, since there is a high tendency that the working substance will bump to each other. So that's why the volume decreases and the pressure increases. So what happens here is that the cylinder is kept in contact with the sink. The piston of the cylinder is moved inwards. The gas is compressed and at constant temperature it's being compressed. The excess heat produced will to flow the sink to make temperature constant. So let's make it constant. So in this process, heat energy from the gas is transferred to the heat sink. So heat energy from the gas, or from here, from the engine, from the gas is transferred to the heat sink. Is transferred here in the low temperature sink, or the low reservoir. That is isothermal compression. So the fourth and the last process is the adiabatic compression. So the fourth and last process is called the adiabatic compression. This is a point D to A. So it is a point D to A. All change in temperature is contained within the system. Since this is an adiabatic, all change in temperature is contained within the system. That is because that is the rule of adiabatic. So the cylinder is kept in contact with the insulating stand. The piston of the cylinder is moved inwards. The gas is compressed such that no heat enters the system or leaves from it. The volume decreases and the pressure increases since it is being compressed. A volume decreases and a pressure increases since it is being compressed. So that is an adiabatic process. So that is the Carnot cycle. First is the isothermal process, the adiabatic process, the isothermal process, and the adiabatic process. Isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. So we have here the formula for the processes. So as you can see in I1 and 2, that is an isothermal expansion. That will give us a Q2 rate, which is equals to Q2 equals to delta U2 minus delta U1 plus work 1 minus 2. So that will give us a Q2 rate. And the following formula that you are seeing in your screen now, we'll be practicing that one in computing a mathematical problem relating to this topic later on this video, maybe at the end of this video. So So that is the Carnot cycle. So why does this Carnot engine and Carnot cycle is an ideal heat engine or ideal heat cycle? Because it is a perfect engine. What do we say by a perfect engine? There is no friction between piston and cylinder walls. Perfect engine because it uses ideal gas, just like that. And there is no friction between piston and the cylinder walls, and no heat transfer between the surroundings and the system. So there is no transfer of heat between the surroundings and the system. That's make it a perfect engine, and that's make it a efficient or remarkable heat engine or heat cycle, heat Carnot cycle. So that's make it more remarkable. So as you can see here, this is a Carnot engine. The point A to B is an isothermal expansion. The B to C is adiabatic expansion. C to D is isothermal compression. D to A is equals to adiabatic compression. So A to B, they're the source. The heat energy comes from the source or from the hot reservoir, and it's being rejected through the cold reservoir here at the point C to D. So this is a Carnot efficiency. This is the heat, the total, the red here, the second diagram or the second photo, the red that covers here are the network area. So, or this is the work output done by the system. This is the work now. From heat to work. That is the network. So that's it. So in summary, Carnot cycle, a cyclical process that uses reversible processes. A Carnot engine, a heat engine that uses a Carnot cycle, and Carnot efficiency, the maximum theoretical efficiency for a heat engine. So again, the reversible process is both the system and its environment can be returned to their initial state. So that is a Carnot principle, Carnot engine, and Carnot cycle. So these are the references. So later in this video, we'll be solving a mathematical problem. So we have here an example number 1. In a Carnot engine, 800 joules of heat is absorbed from a source at 400 Kelvin and 640 joules of heat is rejected to the sink. The temperature of the sink is, so we are trying to find the temperature of the sink. So first, let us identify the given values. So the givens are given. We have the value of the QH, which is 800 joules, and the QC, which is 640 joules. We also have the value of the hot temperature or the source, which is 400 Kelvin, and we are to find the temperature of the sink or the cold reservoir. So for this equation, for this problem, let us use the equation QC over QH is equals to TC over TH. So let us substitute everything. So we have the QC is equals to 640 joules over 800 joules for the QH is equals to TC, which is unknown, over our hot temperature, which is 400 Kelvin. So let us cross multiply. Let's cross multiply this one, and this one. So is equals to 800 joules TC, and then 640 joules times 400 Kelvin will give us 256,000 joules in Kelvin. So let us multiply both sides by 800 joules to get the TC, or the value of our cold reservoir. So this is TC is equals to 256,000 divided by 800 will give us 320 Kelvin. So the temperature of our sink now is equals to 320 Kelvin. So that is an example number 1. So let's proceed. So so let's proceed to example number 2. So calculate the maximum efficiency of a heat engine with operating temperature of 500 degrees Celsius and 700 degrees Celsius. So in this problem, we are to solve or calculate the maximum efficiency. So first, again, let us identify the given value. So the given values are this. Our TC is equals to 500 degrees Celsius. Our TH is equals to 700 degrees Celsius. So since it is in terms of degrees or Celsius, let's convert that one into Kelvin. So TC is equals to 500 plus 273. That will give us 773 Kelvin. And the TH is equals to 700 plus 273. That will give us 973 Kelvin. So next, for this problem, let us use the formula. The efficiency of a Carnot engine is equals to 1 minus TC over TH. So let us substitute 1. We have here the TC, which is, in terms of Kelvin, 773 Kelvin over our TH. This is TH, by the way. TH is equals to 973 Kelvin. So let us divide this one. So that will give us 773 divided by 973 is equals to 0.79. So 1 minus 0.79 will give us 0.21. Since we are trying to find the maximum efficiency, hence, we have to multiply this one by 100 to get a percent. So 0.21 times 100 is equals to 21%. So the maximum efficiency of the heat engine operating in a temperature of 500 degrees Celsius, or in terms of Kelvin, that is 773 Kelvin and 973 Kelvin, will give us a maximum efficiency of 21%. So that is example number 2. So let's proceed to example number 3. So this is the last one. So a Carnot engine is operating at temperature of 300 Kelvin and 600 Kelvin. Calculate the amount of heat energy discarded into the cold reservoir if 12,000 joules of heat energy is absorbed by the engine. And letter B, how much mechanical work is performed by this engine? And letter C, we have to calculate the efficiency of this engine. So first, let us identify the given values. So the given are the TH, which is 600 Kelvin. The TC is equals to 300 Kelvin. This QH is equals to 12,000 joules. And we are to find the QC, or the energy discarded into the cold reservoir. So this is unknown. So for this question, so let us use the formula. The TH by TC is equals to the absolute value of QH and absolute value of QC. So we have that formula. So let us substitute. So we have 600 Kelvin for the hot temperature and 300 Kelvin for the cold temperature, and we have 12,000 joules for the heat being absorbed by the system, and we are to find the absolute value of QC. So let us cross multiply. This will give us, let's cross multiply 300 times 12,000 joules. So we have 3,600,000. And this will give us the absolute, and times 600 Kelvin times the absolute value of our QC. So this one, so let us divide both sides by 600. So 600 Kelvin. So we have, because we are finding this one, so is equals to 6,000. So our QC is equals to 6,000 joules. Sorry for the delayed. So our QC now is 6,000 joules. So that is this is the amount that the heat energy is discarded into a cold reservoir. So in letter B, how much mechanical work is performed by this engine? So letter B. So mechanical work is equals to the absolute value of QH minus the absolute value of QC. So since we have a given value here, so let us substitute everything. So our QH is 12,000 joules minus 6,000 joules. So it will give us 6,000 joules. So this is the work done. It's performed by this engine. So let's proceed to letter C. So our letter C is calculate its efficiency. So the efficiency of this Carnot engine. So let us use the formula TH. The efficiency of this Carnot engine is equals to TH minus TC over TH. So let's substitute TH is equals to 600 Kelvin minus 300 Kelvin over all over 600 Kelvin. So this efficiency is 600 minus 300 is equals to 300 divided by 600 is equals to 0.5. So since we are trying to find through a percentage, so let's multiply by 100. So this will give us the efficiency is equals to 50%. So that is the efficiency of a Carnot engine operating between a temperature of 300 Kelvin and 600 Kelvin. So that's for the computation. So thank you for listening and watching this video. Good day, everyone.